And then if we don't have enough time, you can send us some questions and we will forward them to Professor Wainer. And also this talk will be recorded for those who are not able to attend today. Okay, sorry, Gabriel. So the virtual floor is yours.
Okay, thank you. Thank you, Miguel, for the invitation. It's an honor to be the first speaker. Today I'm going to give a brief introduction to cellular models, which is what we have been doing in the lab, and we will in the end show what we are doing for studies of COVID-19. So this is a very long story. I will try to make it as short as possible. So how do we start? Well, basically in our lab, we've been working using Bernard Stiegler's Devs formalism for a long time now. Everything that we've been doing is one way or the other influenced and associated with research in devs. What is devs and what's this devs formalism? This it's an acronym that stands for Discrete Event System Specification. So it's a formal mechanism for modeling discrete event systems, okay? So it has a mathematical notation that is more or less described here, in which you can describe discrete event systems, and as differential equations model continuous systems, this discrete event system specification describes systems in which time advances using a continuous time base, but the events occur at discrete steps of time. It's not, you don't have continuous events like in continuous systems. Devs has been developed for over 40, 50 years now. And the idea is that you start by building very basic models that are called atomic, that are defined by two very different things, 3 sets here on the left and 4 functions here on the right. And everything that you can do to describe behavior is based on the work of these 4 functions. One of them tells you what to do when you have an external event. The other one tells you how to generate external events to the outside. And there are 2 that are intrinsically connected. One of them is a delay function that tells you how long an event will last. And another one is called the internal transition function that will tell you what will your model do when that time is consumed. The 4 functions can only do the following. They can work on internal state variables. They can use external inputs, or they can generate outputs. The inputs come into a particular set, the outputs go into another particular set. Once you build one of these, you can put them together like in this figure to build something that's called a couple model that share these X and Y sets. So the coupling mechanism has been formally defined, and it's so the semantics of the coupling is it's formal, and then you can build abstract simulation mechanism that will make this run. So you build an atomic model for behavior, and then you couple them together into something called a couple model that puts them together and takes care of the structure. So you can build very basic models and couple them together into very complicated things. You focus on the modeling only, you don't care about the simulation. There is an abstract simulator that will simulate it for you. So this is interesting because these formal techniques will allow you to think about the system before starting programming a line of code, and you can be very abstract and see what you're going to be doing before and early in the process. And it moved from discrete event systems to a full range of dynamic system representations, as I will show in my next slide. The important thing of separating the model from the simulator also gives other advantages. You can build different simulation engines and the same models will run in all of them. The well-defined coupling of components and this hierarchical composition lets you building complex repositories that you can reuse. Start with small things and build them up in a hierarchical fashion, or start the top down with a high level abstract model and then split it in tiny pieces. The interfaces are modular, so you can do standalone testing and build libraries of models. And in the end, this is a very useful method for building models and run simulations. It's been very successful. So this is a slide from Hans van Geloof that I normally use that shows that there has been many translations from different techniques ranging from P3 nets and state charts up to event scheduling and continuous models to like things like partial differential equations or bond graphs into devs. So devs can be used as a modeling language that glues together different techniques to build very complex models using this common modeling method that I quickly explained in 2 seconds in my previous slide. So if you want to study about devs, I can give you lots of tips later. But one of the things that we did was to come up with a new method that is used for modeling cell spaces. The idea is that when you have a physical system problem, and it can be seen as a spatial model. Let's consider, for instance, an event, you know, a social event with a crowd, a rock concert, right? With thousands of people moving around. So we want to divide the space of the concert in geographically divided areas with a certain topology. And we can establish some kind of relationship between a space over there and the neighboring space. So we will call one of these a cell, and we will do something with that cell. We will put a computing device in that cell. So there is a very well-known formalism that does this, which is called the cellular automata, in which you put a computing device in the cell, and then you reproduce the computing device in all of the cells in the space, and they are connected to each other through a neighborhood relationship. In this case, it's north, south, east, and west. And the cell is going to be changing based on what happens in the neighborhood, okay? Based on this, we did a combination of cellular automata and devs and expanded it into this thing that we call cell devs that works more or less as follows. Excuse me. Each one of the cells is a devs model, like the one that I showed before. It's an atomic model, but instead of having all of these complicated functions, we constrained it to 2. One of them that takes care of changing the state of the cell based on inputs from the neighbors, as you can see here. So the cells are connected to neighbors through as a couple model. So you receive inputs over here, you compute a local function, and then you're going to transmit the outputs to the inverse neighbors to influence them. But you don't do that immediately. You do it after a given delay. So when we build a cell devs model, we get one very simple cell. We write a very simple function that will define how state changes according to inputs from the neighbors. And then with a very simple delay function, we can deal with the timing of those events. Each cell can have a different time, and the spread of the outputs of the cell can be done according to this. And it's again a discrete event model. So if there is no activity in some of the cells, you don't compute those particular cells, which makes it run very efficiently. So it's a discrete event cell space. The cells execute asynchronously. So for instance, there is a pedestrian over here, and the cells around it are going to be activated because there's some movement, there's a person moving around. But the other ones don't need to be affected at all because there is no activity around there. We also use an abstract simulation mechanism, so the models can be run in parallel, in distributed fashion, or in real time, and the actual model will not change. Now, in terms of the Delay functions, we have a few ways of defining how these delays work. Let me explain what each one of the cells do. You see something around you. So for instance, this cell is an empty cell, okay? And you see a pedestrian on the cell of the left represented by this input, okay? So your local computing function will say, oh, look at this. There is an individual on my left and I'm empty and the individual wants to come into my cell. So the tau function will say, if there is a person to the left and I am empty, well, what I'm going to do is I'm going to receive the person. So in that precise moment, the person will be coming into the cell and then you will report to your neighbors that you took the person and the other cell will delete the person from it, okay? But now, so depending on who's coming to the cell, some people walk fast, some people walk slower. So we need to represent velocity somehow. So we do this with the delay function. So what will happen is that we will say, okay, this person walks at 1 meter per second. So 1 second after, the person will leave and it will affect to other cells that will receive them, okay? This kind of behavior in which every single movement that you do here, every single change of the cell that your local computing function tau does is spread out is called a transport delay. But sometimes you need preempted behavior. So let's imagine now that, okay, oh, sorry. Imagine now that you are in this cell, sorry, the cell is empty, okay? And then this neighbor comes and says, okay, I want to take your place. And then you say, good, I'm going to receive you. And I'm going to tell the outside world that 1 second after, you are going to leave the cell and you're going to move from left to right. Let's assume that 0.5 seconds into it, the second has not passed. There's someone coming, running very fast. They're coming from another cell. They're coming from the south. So the cell is still empty, okay? Nobody knows that the cell has been taken because I have not reported to the outside world. I need to preempt that state change because what should happen is that in 0.5 seconds, the person should come and go from south to north. And 0.5 seconds after, then I have to do the left to right. So we allow this preemptive behavior with what we call the inertial delay, which basically, if you skip the value of the cell for a given time, it's going to be sent to the outside world. Otherwise, you're going to be preempted, and the one that gets there is going to win and is going to pass. So by combining very simple functions that you have to learn, I know it's been quickly, but today I'm going to give general ideas and then I can guide you to read more if you're interested. But with a simple delay function and a simple tau function, you can model very complex applications. How do you do that? By replicating the cell in a cell space, and then you can even combine cell spaces with each other and even with other devs models that, or even models written in other formalisms, okay, through a couple cell devs. So what do we have now? We have basically a mechanism to define a cell space, a mechanism to define how a cell works based on a tau function and a delay, and a mechanism to couple cell devs models to each other. What do we do with this? We build tools. One of the tools that we use a lot is called CD++. It has an interpreter with a whole language built in that you can use to model all kinds of complex applications, ranging from arithmetic functions up to Boolean functions that will take care of your state, and things like predefined constants. So you can do all kinds of experiments in physics and chemistry, or you can do complex things like crowd movement, okay? So it looks more or less like this. This is a very simple toy cellular automata implemented in cell devs in the CD++ tool. It's called the Brian's Brain. You might have heard about the game of life cellular automata. It's extremely popular. This is a variation somehow of the game of life. It's something a bit more complicated. So as you can see, this is the definition of the couple model. We are saying that this is a cell depth of 400 by 400 cells using this neighborhood, okay, as it's my 9 close neighbors. It's a wrap cell depth, which means that if there is behavior on one end of the space, it will wrap it up and will show up on the other end, okay? And this is the tau function that contains on the right a precondition for the rule, and on the left a postcondition for the rule. So let's see how this works. Let's start by this cell. This means that the current cell is empty, and then there are 2 neighbors that have a value of true. And in this case, your cell will start firing. What will happen? Okay, I have an empty cell, 2 neighbors that are in the refractory state, which is value number, sorry. I have 2 neighbors that are in the firing state, which means that true count is 2. In that moment, I become a firing cell, and my state will change from empty to firing. A few milliseconds after 100 milliseconds here, this is the delay, this will be sent out. And when your neighbor is receiving your information, it will see that you've been firing. So now you're firing and you will become refractory. And after the refractory period, you will be dead again until you see some excitement around you again. In any other case, the cell becomes dead and doesn't do anything. So there are basically 3 states, dead, firing, and refractory. And when you do, and you set an initial set of conditions, you try to see if you find some emergent behavior. This, people who study the Brian's brain will be analyzing this kind of cellular models. And the slide that I showed you 2 seconds ago generates this emergent behavior. As you can see, doing very simple rules, you can come up with models. This is a theoretical model that people use for learning on cellular automata, but you can do very complex models with behavior that emerges with very little effort, okay? Oops, okay, okay. Good. So we have done a lot of cell devs applications. You can find them at celldevs.sc.carlton.ca. I will go very quickly through a few examples in case that you're interested in studying those kind of phenomena. You can go to our website and get started from there. So we have things in environmental systems that I'm not going to show now, and physics and chemistry. This slide shows a couple of models that we built for medical and biomedical application, ranging from the interaction of your immune system with cancer cells, and some combination of computational fluid dynamics and cell devs to study clogging arteries. So you have a clog and you have a clot, and then if you have thickening of your thinning of your arteries because of cholesterol, you can end up having a heart attack. So these are different simulation scenarios for the same clot. And then we've been working on nerve terminal modeling or heart issue behavior. Lots of applications in biomedical systems. This is an example that I show normally on environmental sciences, where we have built forest fire models based on the well-known Rothermel spread equations. And here you can see how we can use complex delay functions. So to the right, we are saying, okay, I see fire in the southwest. Okay, burn. So precondition is fire, postcondition is burn according to the Rothermel rules. But then spreading of the fire will depend on the wind, on the direction, and of course, if you're going from north to south, and if these squares represent 1 kilometer by 1 kilometer, it will take longer to move in the diagonal direction than in north, south, or east, west. So with very simple equations at the delay, you can deal with speeds very nicely. So the timing delay is explicit. Each cell will have a different delay at every moment, and you can deal with complex timing models. We have done this for these forest fire and other environmental systems, like so we studied floods and watershed formations and invasion of pine beetles. And then we did a lot of applications in the field of wireless networks. We had a couple of projects with Ericsson here in Ottawa, and one interesting model that we built, it's the one that I'm describing in this slide, is the diffusion of malware in wireless sensor networks. Basically, we put on each one of the cells a wireless sensor node. Some of them are unoccupied or dead. And what will happen is that normally they transmit with each other. They have batteries that die. And but then there is an attack from something like a virus that will try to attack your WSN. So we ended up building a traditional susceptible, infective, recovered model that is used in epidemiology. As you can see, normally the nodes are going to be susceptible, and if there is an attack, they might become infected and they can spread it out to other neighboring nodes. There are two options. So the malware in those sensor network, what will do is they will try to kill the cell, the node, by draining their battery. So they will start using unexpected computing resources to make the node die. And after a predefined time, they can go dormant to save some battery, and they might be infected and dormant, or they might be infected and they can spread, or they can use a lot of battery and they can die. So we did lots of different interesting studies, and one of the good things of the formalism and the tools is that you can conduct complex simulations with ease and end up with visualization scenarios and interesting analysis from the visuals. So these are different examples of attacks with different topologies and distribution of the networks. I'm showing this one because it leads very nicely to our next steps in our research. But as you can see, everything that we do looks like this, okay? These are the equations that we write, or they look like that, okay? But the simulation engine, you don't see it, it's hidden. You focus on the self-devs model. Behind that, there is a devs model. And the devs model runs a simulation algorithm that has been proven to be correct. And as it's separated from the model, we were able to run it in different kinds of hardware configurations. Years ago, we had a parallel version on a simulation cluster that we built. Right now, we're running it on multi-core computers and GPUs, but the models are never touched. So you develop a model, you put it in a database, and you can run it in your laptop, or you can end up running it into a cluster or in the Amazon cloud, okay? We have done experiments on all of that. The models don't change, which is an extremely powerful property of the self-devs model. And we could conduct experiments in which we were able to improve speed of the simulation results by parallelization of the execution of the models. On top of that, we were able to conduct distributed collaboration in which we could combine a parallel simulation engine and a rendering engine on campus here with a standalone simulation using the high-speed interconnect around the world. In the US, it used to be called the Internet 2. In Canada, it used to be called CANet 4, CANet 5. In Europe, every country have their own. In France, it's called GEANT, and there's a European Union consortia that takes care of that, and we conducted distributed simulation across the ocean. We had nodes in Ottawa and New Brunswick, and then Clermont-Ferrand in France, and I have one of my students in Jordan, and we were running this kind of cell-depth models across the ocean with optical networks to conduct experimentation. The models never change, okay? Then we ended up building cellular models as a service. So we have web services in which, so hidden somewhere, we have a cell-depth simulator, and in the front of the application, we have some kind of geographical information system. So that sample model that I showed on forest fires now has a front end with a Google Map or Google Earth, and it takes data from the web to change the influence of humidity and wind in the model online, and we end up having simulation results on maps. Later, what we ended up doing was also completing it with the acquisition of the data from GIS. So now you get information from a geographical information system. You feed that information to a cell-depth application running remotely, and then you collect the results into the different geographical information using georeference simulation results. I will show an example of an experiment that we did. We got one open source GIS called GRASS. We got a region, this is in North Carolina. We have different information in the GIS, a map of the elevation of the terrain, the use of the land. Here you can see that there is a lake, and around the lake there's shrub and trees, but then all in red. So these are, depending on the color, there are different kind of vegetation, and there are water bodies, and there are roots and houses, okay? So we extract this information from the GIS, we mix it with a cell-depth models that runs remotely the forest fire application, and in the end, we have a combination of the three into a Google Earth application in which we can see the forest fire spreading out in that forest close to Raleigh. This is a snapshot, but as you can see, well, we use Google Earth because you can build these widgets and animate the simulation. And this is all based on weather information plus the GIS that I showed 2 seconds ago. So now we have integration of GIS, distributed simulation running remotely, parallel simulation, and all of that use the same model. The model has never changed, okay? And then going into the COVID direction, at a certain point, we did something similar with a study based on a paper of spread of disease by monkeys, by macaques in the island of Bali in Indonesia. So we got a GIS also, and we extracted a raster map from Bali. And now we have vegetation. The monkeys cannot jump over bodies of water, but they can move around. And like in the wireless sensor network case, we ended up building a susceptible infective recovery model for the pathogens in these monkeys, in which the monkeys are susceptible, and they can be infected, and they can be symptomatic or asymptomatic. They can become immune to the virus. So we built a state machine in CellDevs for that. And we run a wide variety of simulations with areas that have the macaque population infected, and studied how they were influencing each other. And this was a toy example to combine GIS, simulation, and visualization on Google Earth. I don't have it here, right? So we were ready for this pandemic because we had a bunch of models that we have built that could be easily adapted to study the disease. As you might know right now, these kind of models have been widely used to study COVID. So there are lots of variations, and one advantage that we have is that we can very easily adapt the models to a different kind of pathogen. And as everything is built as a devs model, we can do a rapid prototyping very easily, and that's what we did. This is one of the versions of a CellDevs model that we have been running initially as a prototype. This was done in, I don't know, 2 days. As you can see, what we have is 3 groups of rules. One of them to determine if you're going to be infected. So the state of 0 means that you're susceptible and you can get infected. And there is a function that's defined as a macro. I didn't include it in this slide, following the equations from the SER model, that is going to compute if any of your neighbors have an infection and your probability to get infected. And if this one tells you, yes, you are in serious problem to be infected, then you are going to do the following. Another function that will, at random, and using the equations for the SER models, determine if you got infected or not, if you are going to still be susceptible, and is going to spread the disease after 1 day. Okay, so after 1 day that you got infected, you're going to tell your neighbors, oh, I got my infection, and they might get infected too, because now you're going to be one of these guys that was infected. Now, we quickly introduce symptomatic cases that were not in the original SER model. What we did is we included new equations for the asymptomatic cases that will make you sick and will spread out the disease after 7 days. You are 7 days without symptoms, and only after 7 days you're going to start infecting your neighbors. And then once you're infected, this one includes a state for dead individuals, which again, based on the computation for the probability of deaths, it's going to change the model to dead according to this computation. If not, it's going to increase the number of days that you have been infected, and eventually after 14 days, when this number gets to 14, you're going to be considered recovered because you didn't die in those 14 days. So we can conduct experimentation very quickly and do different scenarios with different transmission rates. And in this case, you will see on the left and on the right. So we have different foci and different death rates. Black cells mean that people have died. Green cells mean that people have been recovered. And you can do experimentation very quickly and end up with visual results that are useful for analysis and for sharing the information that you have obtained, and doing trying to help with validation. One of the things that we did was to build I'm going to show that now. Uh, a remote configuration for the models and remote execution. So this model, sorry, so we have a database of models here. I'm going to show you the COVID model with certain parameters that I showed today. So this one picks up a model that we have in the database, and then when it's ready, it sends that to a remote server to be executed, and then we can play back the scenario as a result. But not only that, the result stays in the remote server, and we've been building, so we have been building notebooks. Okay, sorry, give me a second. With Python. So this is an example of one simulation scenario. We have a lot of documentation of what happened, the Python code to see how the plots were generated, and then we can generate plots like the one that you would see in the news every day, and to study the susceptible scenarios and how the disease evolves. And in parallel, you can study it at the individual spatial analysis through the cell depth visualization. Okay. So all of this is open source and shareable. We have lots of videos in our YouTube channel with visualization of the results. And let me show you a simple example of the kind of modifications that you can do. So we have an adaptation of the model because now we have a new tool that can write much more complex cell depth models, and we've been using that. So we got from a couple of papers adaptation for the shared model for the cases in Iran with proper validation. And then we said, okay, let's study now what happens if we put a lockout scenario for Iran in which we have 10 days of lockdown and 4 days in which you go to work. This is a strategy that Israelis are trying to come up with and doing experiments about that. You go to work for 4 days, you go back home for 10. If you got sick in those 4 days, which is the period that you know that you can get sick, you will bring it to home and you are going to see the disease in the next 10 days. And then if everything went well, you go back to normal work for the next 4. So this is a case without control, and these are the case of infections and number of days of infection, okay? So without control, we get to the peak very quickly in less than 50 days. But with the Israeli strategy, it takes over 120 days to get to the peak, okay? And so we have better control of the disease. But then we said, what happens if the government says 10-4 and people are disobedient, which we see it's happening right now. So very quickly, in no time, we introduced 20% of people that are disobedient or 50% of people that are disobedient. And you can see that according to the level of obediency, you might end up having the peak way later or almost at the same time as without a case without any kind of preventative measures, okay? So we can run this kind of simulation very quickly, all based on cell deaths. So what's next? Well, what we're trying to do right now is we have information from Statistics Canada. One of our students worked there, and we have the whole area, well, we have how the whole country is divided, and this is the Ottawa city area. We have the province of Ontario, and this is a subsection in Ottawa. And what we're going to start doing is to combine the shared models with different information that the geographical information system gives you, like access to health or quality of the water in your area or concentration of the population to do advanced experimentation models. And the next thing that we want to do is this. So what you are seeing right now, it's not a picture, it's all fake. It's done by our colleagues in the School of Architecture, and they can do very advanced visualizations. We collaborated so we have a very interesting project that started years ago when they modeled an area in Montreal, and we had CellDev's crowd simulations running over there. And we can have very, these are very precise visualizations that look exactly like the real city section, and we want to integrate individuals over there, but we want to do studies on campus. We have a lot of experience with this integration between this kind of software. There is a tool by Autodesk Research called Revit, but there are others, some of them open source. These kind of tools are called Building Information Management. And we have the beams for the whole campus at Carleton. And we want to study, so in the past we did things like this. These are cell models of evacuations of the buildings, okay? But now what we want to do is something that's more interesting, which is, it's known that when you get the disease, the largest amount of contagion comes from indoor scenarios. So we have built, one of my students just built a tool in which you can upload a BIM file or an image. This is a lab in the university. So you get the BIM file and you load it and you run a simulation remotely. So this is an activation of our RISE distributed simulation engine that runs devs and CellDev's models. There's a version of this running on the Amazon cloud. That one is running in our lab. And basically, once you have loaded your floor plan on the application, you run a simulation, and then you can visualize the results as follows. So this is a case study in which, as you can see, there are windows over here. The windows are open. There are people that are infected, and the fresh air is going to influence how the disease spreads in the room. And we can change the scenario very quickly. We can have a similar scenario with closed windows, which is over here. The closing of the windows is pretty straightforward. As you will see, the windows are there, but they are closed. There is some filtering of air, but as you will see in the corner, the people that's getting infected, while they breathe, they spread out virus, and they can get anyone that's very close infected. Right now, we're very focused on indoor scenarios because this is where we believe that the major issues are going to be happening. In a very quick overview, I have tried to explain how the devs formalism is useful for modeling all kinds of discrete event models, and CellDevs is an extension that allows you to model complex systems that have spatial properties. You can build all kinds of complex models with ease. There's a variety of applications, and then we have long years of experience of that. And the formal definition of the models lets you think about what you're going to be doing before coding anything. You can define the equations and find errors in the equations, just fighting with your colleagues. And then when you implement the same equations. Timing is very complicated to define in many of the applications, and it's trivial in this case through inertial transport delays and combinations. It's a discrete event model, so you can run models very quickly and through parallel simulation even faster. Students learn really fast. It's not too complicated. you don't need to explain all of the theoretical aspects of devs. You can focus on the tools, show examples, and go from there. We have undergrad students in third year that are in the room that were able to reproduce and modify some of the models that I showed today in less than 2 days. Everything that we are doing is open source, and it's in our CellDevs website. We have videos on YouTube. We post news on our Twitter feed. Right now, as I mentioned, we're trying to work on the integration with GIS and BIM models to work hard on indoor scenarios. We have a collaboration with a company that will give us sensor data in real time to combine these with the models that I have presented earlier. And I think that's all for my presentation. I'm thanking all of the students that have participated in the research and have given me some of the materials that I have presented today. And I'm also including a colleague in the University of Buenos Aires that has developed some of the earlier shared models that I presented today. And thank you again for having me. And now I think we have time for questions. Thank you, Mike, again.
Thank you very much, Gabriel. Very amazing talk. I can conclude. It's really great what you are doing there. A lot of effort, and the potential is really amazing. I think we have just time for a couple of questions. If the participants have a question, please raise your hand. I also have received a couple of questions. Okay, there is one from Paolo. I will unmute him.
Okay.
Hello, Paolo. Can you introduce yourself and make your question, please?
Hello, this is Paolo from the Amsterdam University of Applied Sciences. And so first of all, thank you for this great presentation, Professor Wainer. Very interesting. And my question is more on the modeling side. So as far as I understood, you have built this formalism, devs, by using the cells, okay?
Mm-hmm.
And usually when you build your model, you need to choose the level of abstraction of your model. Can be detailed or can be less detailed, okay?
Yeah.
Am I correct if I say that by changing the size of your cells, you are basically changing the level of abstraction of your models?
Yes, it's absolutely like that. So, so for instance, we are going to be working on different levels, and I showed all of the levels over here. Okay, so in this example, we are at the level of a room, and in this case, every cell is approximately 50 centimeters by 50 centimeters.
Mm-hmm.
So in this case, what you're going to be studying is the accumulation of virus pathogens in the air with people breathing in and out. So the models here are people, so they describe the accumulation of viral particles through breathing, okay? So that's one level of abstraction. Mm-hmm. And we're not going to use a shared model in a room because it's going to be a modification. It's not the same, okay? Now, I'm trying to stop this and going backwards. Oh, sorry. Okay, so let's say over here, okay? Mm-hmm. So we have, in fact, let me open a website, okay? So, our project is at the campus level. This is the BIM of Carleton University. What we're trying to do right now, it's at a different level. So yeah, as you can see, there is a train over here and the students come and they go to different buildings and we're going to have pedestrians there. And some of them are going to be sick. Some of them are going to go to those rooms And so when they get indoor, they're going to be doing something. But what if there is a party here? It's, and there's a concentration of students. So the level of abstraction there is going to be different, and it's not going to be accumulation of particles at 50 by 50. Probably we will be working at 10 meters by 10 meter scale. And now this university campus is part of the city of Ottawa. And the city of Ottawa, something that's interesting is that the topology of the cell depths doesn't need to be square or hexagonal. We can use these polygons. So we can do cell depths in which a cell is this polygon and the other cell is this polygon. The only thing that we care about is that there is a neighborhood relationship between them. And when there is a certain amount of disease concentration in this, well, the probability of contagion in the next area of the city is going to be higher or lower. Different scales and different abstraction of the model. So of course, it's not going to be the same model. We are going to be working on different instantiations of the shared model, but we're interested in putting all of them together because so you take the train from your sick neighborhood to the university, and you get off the plane, and then the train, sorry, and then you go into your building, and then in your building you go into your room, and in your room you start breathing. So through cell depths we can connect one cell depth with the other, and each one of them at their own different level of abstraction. You cannot use this model to model the city or the whole country, right?
Yes.
So, yeah.
Thank you very much.
Thank you. Thanks for your question.
Okay, Gabriel, I have two more questions that I received. One is from Margarita Bagamanova. She is from the Amsterdam University of Businesses, of the Amsterdam University School of Business. And she was asking, what are the main limitations of using such cellular model?
So I don't have many limitations. That's the truth. I don't know. We've been working on this for a long time, and there are really no. So we were adapting the science that's in the field in no time, and we were integrating this with different scales of geographical systems in no time, and it's been done by undergrad students and postdoctoral fellows at different levels of difficulty. To me, it's so one of the interesting things is that we can contribute very quickly with the community. One thing that's missing, I would say, but it's not a difficulty, is we need libraries of models. If we had, and we are building them, but we need to come up with a mechanism to have be ready to use libraries of models they can be adapted for different applications. Luckily for this case, we had a few, and we were able to adapt them in no time, because we had other models for avian flu and for dengue fever. So doing an adaptation for COVID, once you have a library, is more or less trivial, right? Yeah, so, yeah.
Okay, thank you. So if I understood or the way I see it probably is that in particular, this technique of cell depths is perfect for spatial models, right? Because for instance, for other type of simulation like manufacturing, logistics, probably they are not the perfect fit, right? What do you think?
So yeah, today I talked about cell depths because we were interested in spatial, but we also have libraries of devs, okay? So right now in the project, we have a number of students studying indoor spread of the virus, and then outdoor, contact in campus or cities, okay? And, but also, we are building a traditional served model that is not spatial. It's so it looks more like, I would say, like this. It looks more or less like this, okay? In which the compartments, so in each atomic model, we have the compartments, and if you give me a second, no, I have a, give me a second, maybe I can show you something interesting. Oh, I don't have access to, give me one more second, okay.
Okay.
Yes, so basically these devs models can be, okay, because my students, yes, this is, okay, good. So these devs models can be applied to any application, okay? So for instance, in the kind of applications that you are more interested on, let's take a look at this. For instance, this is an elevator, okay? This is a visualization of a state machine built with the same tool, okay? And it shows the evolution of the different states in the finite state machine for people getting into and out an elevator using the same technology. Something like, okay, temperature control in a building, okay? So some of these are coupled models, some of these are atomic models, and then you can do a more traditional type of queuing system application, and it's all built on devs, but then you can combine this with the spatial if you wanted, okay? Now, in terms of the COVID, so my postdoc, she is working with a team at Polytechnic of Catalonia. You know Pau Fonseca, that he goes to winter symphony all the time. Yes, so so this is a devs model, and Pau has an SDL model, okay? So Pau has an SDL model of, I'm going to stop this. Pau has an SDL model of COVID-19, properly validated with Barcelona's real world data. And so he has the model, he ran the simulations in SDL, and he knows devs. So Christina and himself built a devs version of the SDL. So now we have two different versions of the same shared model with the same baseline results. And we can do experimentations on devs or on SDL and cross-check the results. And these models have nothing to do with space. So you can do whatever you want on that. Yes, it could be used for, I don't know, a queuing system in a supermarket and see if you're going to infect someone else and you don't care about the spatial properties of the model. You care about there's someone infected, you've been there for 20 minutes, you sneeze on someone and that person got sick. You know what I mean? I hope that this answers your question. I don't know.
Yes, thank you.
Yes.
Okay, Gabriel, I think we ran out of time actually. So we want to thank you again for your amazing talk. We had the honor to have you as the first speaker in this best virtual seminar. So we send you a warm applause and we thank you again. Thank you all the attendees for this for coming to this first talk. Please, if you want to know, if you want to be notified of the next presentations of the coming months, please register to the newsletter in the web page. Our next speaker will be on the 17th of July. Is Professor Williams from Michigan University in the US. So thank you all, and have a nice weekend. Thank you, Gabriel, again. Have a nice weekend.
Thank you, Miguel, again for your invitation. It's an honor for me. And yes, thank you everybody for attending. And it's a pleasure.